Like an endless ribbon in different widths and lengths, our highways stretch out in all directions. Where one leaves off, another begins. Built over water, underwater, and even on stilts. Only an ocean can stop them. Most people take our roads for granted until they break down. And no matter how well our roads are built, man and nature seem determined to break them apart. There is a constant matching of strength between the stability of the pavement and the stress it must sustain. The results you know only too well. Constant abrasion, impact, and weathering lead to raveling and flexural cracking. In due course, the durability of the road is threatened, and the protective binding and sealing of the surface course gives way to the constant traffic stress and weathering. Summer heat invites softening. Rutting is a continuous problem, and so is shoving. Winter brings impact stress as the asphalt is embrittled. Even heavy-duty pavement is hard put to stand up in bus stops, on bridge decks, and curbing. Even a smooth landing puts a severe stress on airport pavements. And so does the blast of the engines. Well, we do have our road building problems today, but the fact is that we've always had them. In the old days, even automobiles had problems in taking off and in landing. Two-way traffic on a single lane is a problem. For all we know, they may still be there. It is a grim thought, but these fellows came to the rescue. If these techniques provoke a smile today, what will our present techniques look like 50 years from now? And the same goes for our traffic conditions. The conditions obviously change, but serious problems always remain. Today, we've got our fair share. This film is about some of the steps you can take to help solve some of them. To build a better road for tomorrow, you have to plan for it today. To date, the most universally serviceable road material has been asphalt. Like all materials, asphalt has its limitations. However, some of these limitations can be reduced by the addition of asbestos to the mix. Paving engineers are agreed that to increase the durability of a flexible road, we must somehow be able to increase its asphalt content without, at the same time, reducing its stability. The addition of 1 to 2% of asbestos fiber to the mix permits an increase of 25 to 35% of asphalt without sacrificing stability. Under certain conditions, an increase of up to 50% in asphalt is possible, with no loss of pavement stability. At the pug mill, the addition of asbestos to the asphalt mix calls for little change in operations, regardless of the type of system. Determined by years of testing, a grade of fiber has been developed that is particularly suited for this special purpose. It is simply added to the batch as it is being mixed. To the eye, the asbestos mix looks like any standard mix. It just bulks up a bit more. On the job, too, the asbestos mix requires no special handling. Standard equipment is used, and the crew follows standard procedures. There are, however, some significant differences. The roller can follow immediately behind the paver, and the pavement compacts without flushing. The mix is more workable and is easily placed. Note how the edge holds its shape. And the traffic can go back on the road immediately after the roller with no ill effect. This, in brief, is the story. And all over the United States and Canada, more than 150 state, county, and city highway authorities are currently using and evaluating asbestos asphalt pavements. Research and field tests continue to confirm the value of the asbestos additive. More and more highway authorities are building test strips suitable to their particular problems and conditions. The results justify a closer look at the nature of asbestos fibers. One of the world's major sources of high-grade asbestos, a natural mineral, is the Jeffrey Mine in Asbestos, Quebec. From this open pit comes nearly 1/3 of the free world's supply of asbestos fiber. At the nearby mill, the crude ore is crushed and processed to extract the fiber. And it is refined many times until it meets the rigid specifications set for each fiber grade. As you can see, the asbestos fibers occur in veins that run through the rock formation. The individual fibers are so fine that it takes an electron microscope to magnify them for study. By their natural chemistry, asbestos fibers resist weathering and retain remarkable strength over a wide range of temperatures. They have greater tensile strength than any steel wire of the same thickness. Combined with asphalt in roof shingles, asbestos fibers protect our homes. Used in asphalt floor tiles, the fibers provide flexural strength to absorb impact and abrasion stress. In roofing, asbestos felts are so effective in weathering that they are guaranteed for more than 20 years. And these same natural characteristics of asbestos fibers lend themselves to use in heavy-duty roof decks, joint fillers, bridge planks, and many other applications. In short, the ability of asbestos fiber to successfully resist impact and weathering stress is comparable to the stress to which bituminous paving is subjected. At the Jeffrey Mine in 1953, this observation led to an experiment aimed at solving a severe road problem. The mine roads broke down continually under the pounding stress of 65-ton truckloads moving 24 hours a day, the constant abrasion of crude ore spillage, and severe northern weather variations. JM engineers paved the road with asbestos asphalt. A standard bituminous strip was built at the same time as a test control. The standard pavement showed marked stress within 3 years. The asbestos strip, on the other hand, was still in good condition at the end of 8 years, when it had to be torn up to enlarge the open pit. But the test had proved the point, and Johns-Manville decided to undertake a thorough study of asbestos asphalt pavements. In 1959, the JM Research Center, one of the country's major industrial labs, started an intensive research program. Through many years of product development, the lab had perfected many techniques for testing asbestos asphalt properties and applications to road paving. A summary of the findings is presented by a representative of the Johns-Manville Research Center.
Paving engineers from long experience with standard bituminous pavements are first of all concerned with the stability of an asphalt mix. Used extensively, the Marshall stability test data generally demonstrates that asphalt can be increased with the use of asbestos. The field performance data accumulated shows that asphalt content need not be limited to Marshall optimum values. Pavements with additional asphalt are providing excellent heavy-duty service. Beam stabilometer and cohesiometer tests are part of Johns-Manville research investigation. How does an asbestos asphalt mix test out? In short, the standard basic tests of the paving engineer demonstrate that an asbestos asphalt mix 25 to 35% richer in asphalt than standard mixes maintains its stability. By their very conception, however, the Marshall and Beam tests are designed to test stability and provide no index of durability. For this and other factors, we have had to turn to our experience in testing other asbestos asphalt applications. Here, for example, is a standard weatherometer used in testing asbestos asphalt weathering capacity. Compaction of samples to void contents and densities specified by each state and city is accomplished with a gyratory compactor. Modifications to the standard Marshall test have been made to study deflection characteristics of varied materials. Recording the load carried and deflection of the sample at cracking provides answers as to the improved flexural strength of asbestos mixes. The behavior of asphaltic mixes under simulated traffic is analyzed in repeated loading devices. The degree and duration of load can be varied to duplicate traffic conditions ranging from residential streets to busy expressways. Sample A shows the successful performance of an asbestos mix under 20,000 load cycles, while the standard B mix failed. One of the most interesting experiments on mineral admixtures that has been conducted was a study undertaken by the American Oil Company. Sections of paving using various mineral admixtures were made under laboratory control, then mounted on this full-scale traffic simulator to test the dynamic load strain properties of flexible pavements. The full spectrum of highway stress conditions were created, including varied temperatures, tire pressure, and wheel coverage. Under very heavy traffic conditions, asphalt content was increased up to 50% above the standard optimum value. Only the asbestos admixture safely stood up to the 50% increase in asphalt. In short, this is the way the research evidence adds up. General durability and stability problems existing in many bituminous pavements can be solved with the addition of asbestos fiber. Poor durability, resulting from the inability of the mix to accept sufficient asphalt, is solved with no loss in strength. Stability problems can be cured by this new material, which resists rutting and shoving even under high summer temperatures due to the increase in viscosity of the asphalt cement. And since the experiment at the Jeffrey mine, many field tests have been conducted with the cooperation of various highway authorities, and they bear out the laboratory observations.
Here, for example, is a test strip in Manville, New Jersey. It was constructed in 1959. An adjacent and comparable standard asphalt pavement was placed simultaneously. On the right is the standard pavement after only 3 years of service. The raveling is clearly visible. On the left is the asbestos asphalt surface. A test strip in St. Louis, Missouri, built in 1959, yields the same results. On the right is the standard test control pavement. On the left is the asbestos asphalt, both after 3 years of use. The difference speaks for itself. In short, the increased asphalt in the asbestos matrix helps cope with a problem paving engineers know only too well. Insufficient asphalt leads to an excess of voids and hardening. This leads to raveling and deterioration. The initial stability of a standard asphalt mix is only a partial index of its durability. For the paving engineer, this is common knowledge, and the moral is clear. The results to date justify the testing of asbestos additives under local conditions in various types of applications. One of the major applications of an asbestos asphalt matrix is in thin overlays as a replacement for conventional seal coatings. The addition of 1 to 2% asbestos permits a 25 to 35% increase in asphalt. The result is a tighter and impermeable surface that is more resistant to raveling. The overlay extends the useful life of the existing pavement, and a smooth riding surface is restored with a minimum of effort. The operation is a boon for residential neighborhoods. There is no flying aggregate and asphalt to mess up lawns and living room carpets. And traffic can follow immediately after the roller. The skid resistance of thin overlays has been tested by standard procedures using a fifth wheel assembly and a Wagner stopometer. The pavement is continuously flushed with a fire hose. In spite of the increased asphalt in the overlay, the tests have proved that the coefficient of friction of the original pavement is maintained. Heavy-duty bus stops are another and quite a different application of the asbestos asphalt matrix. Usually about 3% fiber is added to the mix. Extruded curbing is still another application of an asbestos asphalt matrix. The asbestos additive has solved the major problem of the slumping off of the mix. These mixes have been extruded at 340 degrees Fahrenheit without ill effect. In addition, downtime while waiting for the mix to cool is eliminated. Most important, the asbestos curbing has improved durability and indentation strength. And an asbestos asphalt matrix is advantageous in a wide variety of other applications. On heavily trafficked bridge decks, coal patch maintenance of local roads, extra heavy-duty airfield pavements. Applications such as these are being put to the test under many local conditions. Let us hear from a few of the officials involved. First, Mr. Vinton A. Savage, engineer of primary highways of the Maine State Highway Commission.
We have some pretty severe weather conditions here in the state of Maine. We are currently giving asbestos paving a series of rugged tests. One of them is a heavily traveled road on a 14% grade using poor aggregate, right at the Canadian border. Another is a thin overlay using some very heavy traffic. In a third, we are testing how much we can safely increase the asphalt and maintain stability. Next year, we've scheduled curbing tests. We're after increased durability, and thus far, the performance is up to what we'd hoped for.
Next, Mr. Paul Martin of the General Crushed Stone Company, Easton, Pennsylvania, speaking from the vantage point of the hot mix producer.
We have experienced little difficulty in producing asbestos asphalt mixes. No modifications of our plants were required to handle the fiber, as we were able to use the regular filler feeding systems. Mixing the material is accomplished in the same manner as any other asphaltic concrete. Perhaps the only difference is that the same weight piles higher in the truck bodies. There's a definite bulking of asbestos asphalt mixes before compaction. Considerable interest in this type of material has developed in our areas, and the results have been excellent. To those who have not tried asbestos asphalt mixes and who desire smooth, stable, watertight pavements, we highly recommend that they find out for themselves the potentialities of asbestos in asphalt paving.
Finally, Mr. Kurt Watrous of the Peckham Road Corporation, White Plains, New York, with a word from the contractor's point of view.
We've done several jobs placing asphalt asbestos paving material and have been thoroughly satisfied. The reception in our area has been very favorable. We use our regular paving equipment and labor and more or less the same techniques. Certain characteristics of the material makes it easier to place than other mixes. We're able to maintain our rolling equipment immediately behind our paving machine, and traffic can actually follow behind the roller without marking or displacement. Naturally, we take care to prevent this as much as possible. The surface strength is obviously much greater, and we feel that the use of asbestos in asphalt mixes imparts continuity that greatly retards cracking and increases the life of the pavement. We have recommended it highly in the area we serve.
Well, that's the story. How about you and your road problems? Obviously, an asbestos additive is no cure-all, but one thing is clear. Change is inevitable. To stand still is to fall behind. One way to meet the problems of tomorrow is to test today. You'll know what asbestos additives can do for you when you test them under your particular conditions. Asbestos will aid in solving highway pavement problems such as weathering, flexural fatigue, raveling, flushing, shoving, rutting. Asbestos additives will increase pavement durability and will stand up better to traffic stress and weathering. Use them for all heavy-duty pavement applications. Joint fillers, coal patching, curbing, and thin overlays. Let the experience of Johns-Manville paving engineers, gained all over the United States and Canada, guide you in planning and building asbestos asphalt test applications. Johns-Manville is hard at work today to assure the highest standards of service from the highway systems of tomorrow.